Okay, hello everyone. Good morning, all of you. So we start with a great quote from the great Swami Vivekananda, and he says, "Never say no, and never say I cannot, because you are infinite. All the power is within you, and you can do anything."
Good morning,
And
sir.
so everybody has infinite potential, right? So only thing is, many times we don't identify because of lack of confidence. But there is nothing to lose the confidence because everybody has infinite potential. Only thing is we have to learn tapping with it. And today is the birthday of GRKGupta Narasimhara. He is a great personality in Andhra Pradesh, and I think there won't be anybody who doesn't know about him. And he is a Telugu Avadhani. He is a literary performer in Andhra Pradesh, India. Avadhanis are respected for their abilities to spin out verses confronting to Telugu grammar on literally any subject that audience may throw at them as a challenge. You ask any question in any field, and he will be able to answer it. That is the capability of Avadhani. So they are widely respected for their extreme abilities to memorize beyond normal human capabilities. In 1996, he performed Avadhanam with 1,116 Pruchakas. Pruchakas means who ask questions. Right? There are people, 1,116 people who ask questions for 21 days. Right? So he has started answering them. And he also delivers lectures on personality development based on Hindu culture and way of life. And he is very, very famous. There will be a lot of TV programs uh, with his lectures and all. Okay, today we are going to have the eighth class and on energy equation. And last class we were doing these things. We have done the derivation of the momentum equations. And so we got in general, if I write in vector form, so in non-conservation form, rho dV by dt plus del dot rho dV is equal to minus del t plus okay, something like this. This is the vector form, and actually this is divergence of a tensor. Okay, you might not have heard about it. So it will have 9 components, as I told in the x equation: dou tau x by dou x, dou tau x by dou y, dou tau x z by dou z. In the y equation, you will have dou tau x yx by r, dou tau x by dou x, dou tau yy by dou y, dou tau yz by dou z, like that. So you will have total 9 components, 3 components in each. And here it will have 3 components, one in each equation: minus dou p by dou x, minus dou p by dou y, minus dou p by dou z, like that. Here this will have rho bx, rho by, rho bz in 3 equations. And here dou of rho u square by dou x, dou of rho uv by dou y, dou of rho uw by dou z in the first equation. Like that you will have other equations. And this is clear: rho du by dt, rho dv by dt, like that. Okay, this is the way we get the momentum equation. And we have seen the stress strain rate relations, right? And I think these are the equations we have developed, the momentum equations, and these are the stress strain relations. Okay, lambda del dot v here. So del dot v is nothing but epsilon xx plus epsilon yy plus epsilon zz, which is volumetric strain. So all sum of the linear strains in all the 3 directions will become volumetric strain. And here 2 mu epsilon xx, 2 mu epsilon yy, 2 mu epsilon zz, and here 2 mu epsilon xy, 2 mu epsilon yz, 2 mu epsilon zx. And here out of these 2 unknowns, again if you get a relation by Stokes hypothesis, 3 lambda plus 2 mu equal to 0, or lambda equal to minus 2/3 mu. Okay, this is the way we get the equations in closed form, because all the stresses are expressed in terms of primitive variable or velocity gradients. Okay, and then Okay, stresses in terms of velocity gradient, Stokes hypothesis. And then we have expressed the Navier-Stokes equations in non-conservation form and in conservation form. So only thing is the difference between non-conservation and conservation form is based on only the left-hand side. Okay, so this rho dV by dt, how this is expressed based on that. Okay, so this is non-conservation form. If you write this in dou v by dou t plus okay, this will not be there here. Okay, so this will become dou v by dou t plus v dot del v. This is non-conservation form. If you write in conservation form, this will become dou of dou v by dou t plus del dot del v. Okay, so this is the difference between non-conservation and conservation. Right side, it will not change. Only in the left side, it will change. Okay, and in the vector form and all different forms we have discussed. And in strong conservation form also we have written, that is bringing all the x derivatives to the one side and y derivatives together and z derivatives together. And then we have expressed in the matrix form, strong conservation or matrix form. So that I will show you later after the energy equation. And then we have seen how to get the Bernoulli equation from the Navier-Stokes equations. Okay, these are the things we have discussed. And then we'll come to the energy equation. Okay, this is the energy balance. Again, the same thing. The rate of change of total energy of the system is nothing but the local rate of change of energy within the system or within the control volume plus the energy that is leaving the control volume or the rate of work done on the element by both body and surface forces. The main thing is here the equation will be a bit large because energy is a scalar. Okay, and so we have to see the energy in all the XYZ directions by all the body forces and all the surface forces. So we have so many terms in X momentum, Y momentum, and Z momentum, and we will have all the terms together in the energy equation. So it will be a bit huge. Okay, so the rate of change of energy inside the fluid element is because of the net flux of heat into the heat element, and this is actually, as I told, so the net flux given to the system and net work done by the system. Okay, so this is things, and this is the total rate of change of energy in the system. And so this total energy usually will be written as, this is internal energy plus the kinetic energy. And all are per unit volume. Actually, this should be M, right? And per unit volume, if I take, then it will become rho. Okay. So this is the way we get, and we have to see what is the net heat transfer and what is the net work transfer, and we have to equate it to this. Okay, so that is the way we have to go about. Okay, net flux of heat into the element. So this is rate of change of energy inside the element. So I have given it as positive. So this is increase in the energy. Increase in the energy, why it happens? Because there may be heat into the element or work done on the element. Okay, if it is by the element, it is negative. So minus of that we will get positive like that. And so if I want to see what are the work, what is the work done by body forces and surface forces, so we have to see these things. So force into velocity is the energy, okay, or the work done. So here there is tau xx dy dz. Previously for momentum equation we have written like that. Into u we have to write, and up dy by dz, p dy dz we have written for momentum equation. Into u we will get for the energy equation. And you have to be careful about the arrows. So for pressure, it is towards the element, and this side also towards the element. It is Pu dy dz. This is Pu plus dou of Pu by dx, dou x dx dy dz. And u tau xx dy dz, here u tau xx plus dou of u tau xx dou x dx dy dz, like that. And this is away from this element, and this is away from the element. So if you see the difference between this and this, you will get minus dou of up by dou x dx dy dz. And for the stress, dou of u tau xx by dou x, positive you will get, like this. And on the y plane, you will get dou u tau by x by dou y, and on the z plane, you will get this. So this is the total work by the surface forces in the x direction. So in that way, you will have for y direction and z direction, and I have to take the whole. So minus dou of up by dou x, minus dou of vp by dou y, minus dou of wp by dou z I will get. In this way, this tau xx, u tau xx, you will get v tau xx, v tau yy, sorry, v tau yx, v tau yy, v tau yz in the y direction. Like that I will get. So you will get all the things together, surface, body and surface forces. This is, this is pressure force, and this is the viscous force. And body force, you will get rho f dot v dx divided. What you will get is ufx in the x direction, vfy in the y direction, wfz in the z direction. All of them together, it will become f dot v, okay, or b, whatever you say. Here, rho bx dx dy dz plus rho by rho bxu, rho byu dx dy plus rho bz w dx, and all of them adding together rho b dot v dx. And per unit volume, when you take, actually this is m. Okay? Per unit volume, if you take, finally it will get like this. Okay, so this rho b dot v, like that will get. Okay, actually this is for volume, this total per unit volume. If I take this dx dy dz, this dx dy dz goes off. This is the C, that is the third term here. And net flux of heat into the element, it is because of conduction. So conduction, it will be like this. Q dot x will be entering. So this is heat flux. Heat flux means heat transfer per unit area. So into d by dz will give the total heat going into the element. And what is leaving the element? Q dot x plus dou of Q dot x, this is dou x, okay? Dou Q dot x by dou x dx dy dz, like that. So you will have again all the three components. So you will get like this. Dou Q dot x by dou x plus dou Q dot y by dou y plus dou Q dot x. This is minus, okay? So this is leaving, this is leaving. So net flux entering will be minus of this. This will become minus, right? So minus dou Q dot x by dou x will. So you will get like this. This is the heat transfer by conduction into the element. Okay, and if you take heat generation per unit mass as Q dot. Okay, so per unit volume, it will become rho Q dot. Okay, it is like Q dot is per unit mass. So into mass means rho dx dy dz. This is mass. And per unit volume, if I take, this goes off, it will become rho Q dot. So I will get this. And what is Q dot x, Q dot y, Q dot z? This is heat conduction, right? Through the x plane, this is y plane and z plane. And what is this from the Fourier's law? Q dot x equal to minus k dou t by dou x. Okay. Q dot x equal to minus k dou t by dou x. So that if I substitute, similarly, q dot y equal to minus k. So that if I substitute here, this minus becomes plus. So this becomes dou by dou x of k dou t by dou x, because q dot x is k dou t by dou x, dou by dou x of k dou t by dou x, dou by dou y of k dou t by dou y, dou by dou z of k dou t by dou z. Okay, this is the total heat transfer into the element. And per unit volume, if I take, actually dx dy dz goes up. And so this is the, as I told, the time rate of energy of the fluid element. And so this is equal to sum of those two. So if I write in this way, you will get it. The whole total energy equation, rho d by dt, E plus V square by 2. This is equal to, this is the total heat transfer into the element, and this is heat work done on the system. Okay, so this is the way we get. And is that clear for everybody?
Yes, sir.
Yes, sir.
Yeah. And this is non-conservation form. For conservation form, again, this will not change, but this will change. So this will become like this. Rho d by dt of E plus V square by 2, we know that it has two components, local and the convective. So if I write, I will get this. Okay. And this is the whole total energy equation in the conservation form. And so this is dou by dou x of rho into E plus V square by 2 u, and dou by dou y of rho into E plus V square by 2 v. Like that, I will get three components here. Okay. So now if I want to write it in matrix form, so dou by dou t term is there, and dou by dou x term, here one will be there, here this is one, and this is one, and this is one. Okay. So shear stress will be there, and pressure term will be there, and heat transfer will be there, and the convection term. All the terms together, it will come as x derivative, y derivative, z derivative, like that we have to write, and then we can put it in the matrix form. So that you will get something like this. Okay. So this is a mass equation continuity, x momentum, y momentum, z momentum, and then this energy equation is written here. Actually, there will be here shear is not there. It is not written. I don't know how it is missing. Okay. So here that shear stress terms also will be there. And if I write in the matrix form, it will be like this. Rho into E plus V square by 2. This is in time derivative. And in x derivative, you will get rho E plus V square by 2 into u you will get here. Okay. In the next, in the y derivative, into v you will get like that. So plus pu, because on the right hand side it is minus pu, it comes to the left hand side plus pu. And k dou t by dou x, it is plus on the right side, and it comes to the right left side, it will become minus k dou t by dou x. In the same way, all the shear stress terms are positive on the right hand side. If you bring it to the left side, all become minus u tau xx minus v tau xy minus w x tau x theta. So this is the x derivative term. In that way, you will get y derivative term like this, and again you will have v here and w here. So the remaining things will be as it is, and this is j. Okay, 0 rho bx, rho by, rho bz, rho b dot v is this. Okay, plus rho q dot. Okay, so this is the total equations, all in matrix form or generic form or strong conservation form. This is the way we can express the equations. So this is the complete Navier-Stokes equations. As I told, we will see those points also. In fluid mechanics, if you study, they say momentum equation is Navier-Stokes equation. But in CFD, all the equations together, this whole matrix, right? Continuity, momentum, and energy equations together, we call them as Navier-Stokes equations. Navier-Stokes equation solver means solving of all the 5 equations together. Okay? So that is more important. And then here we do a little bit of exercise again. And this is total energy equation we got, but I want energy equation only for internal energy. So somehow I have to take out this, we have rho
d by dt of E plus V square by 2.
So I want to subtract rho
D by dt of E square by 2.
so that I will get rho dE by dt. And how do we get this? V square is nothing but U square plus V square plus W square. Okay. And if I take the derivative of this, okay, d by dt of V square by 2. D by dt of this by 2. So this will become 2u du by dt plus by 2. Okay. U du by dt, v dv by dt plus dw by dt. Rho will be there. Okay. If I put rho there, like this. So what I will get is rho into du by dt plus dv by dt plus dw by dt is nothing but rho d v square by 2. Okay, this I have to subtract from this. Okay, so rho du by dt is x momentum equation. Rho dv by dt I will get in y momentum equation, and rho dw by dt is the z momentum equation on the left hand side. So multiply x momentum equation by u, multiply by okay, u, v, w. Okay, so like that we have to do, and that is done here. So if you, this is the x momentum equation, I multiplied by u. So this will become d of u square by 2, because u du by dt, it will become d of u square by 2 by dt. And so minus dou p by dou x plus dou tau x as well, like this is there. Multiply by u to all the terms. And in the y momentum equation, multiply by v in all the terms, multiply by w in all the terms. So we get this. If you sum of these three will give you rho d by dt of capital V square by 2. So sum of all these things. And if I subtract from the whole energy equation, okay, so this is the sum of all these three equations. So I will get like this. And subtract this from the whole energy equation. I am going to get rho dE by dt. And if you see here, this will not change. Whatever is in the total energy equation, this heat generation will not change, and this conduction also, it will not change, right? Because those terms are not here. But if you see here, u bx, v by, w bz, right, that you will get in the sum. And in the energy equation, total energy equation also, same term is there, which gets eliminated. So that gets cut off. So this is one important point. In the internal energy equation, there will not be any effect on the internal energy due to body force. That gets eliminated. And the pressure here in the total energy equation, you will have dou of pu by dou x. Okay. And here in the sum, you will have u dou p by dou x minus u dou p by. Okay, if you have dou of pu by dou x minus u dou p by dou x, you will get p dou u by dou x. It is something like dou of pu by dou x minus u dou p by dou x. Okay, this is from the total energy equation. This is from x momentum equation multiplied by u. You will get p dou u by dou x. Like that, p dou v by dou y and p dou v by dou z you will get that. And some of these things will get like this, minus p into dou u by dou x plus dou v by dou y plus dou w by dou z. This is nothing but del dot v. Okay, this is del dot v minus p del dot v. It will become
P del dot.
like this. Okay, because it is actually minus of minus, it will become plus, and that's why all these things will be minus, and we will get minus p del dot. So like that you will get. And other things, so if you see these terms, I will get in the total energy equation. In the total energy equation, we have dou 2u tau xx by dou x. And in the x momentum equation, you will get tau xx by dou tau xx by dou x into u. We are subtracting, right? So what will you get here from this tau xx into dou u by dou x you will get. So like that, 9 terms I will get in that way. You will get tau xx dou u by dou x, tau yx dou u by dou y, tau zx dou u by dou z, like that all these 9 terms will be there. This is the internal energy equation. Is this clear?
Yes, sir.
Yes, sir.
Okay. And you have derived a 3-dimensional heat conduction equation in your heat transfer, right? I can get that equation from here, okay, from this equation, right? And okay, because normally you deal with incompressible flow, P del dot V, this becomes 0. And you are not considering viscosity also in the heat conduction equation. So this will become 0. And in this, actually I have unsteady term and convective term. And you are not considering convection in the heat conduction equation. So that will not be there. So what will it become? Rho into dou E by dou T. Okay, whatever convection term is not there, that will be 0. Okay, and this will be there on the right hand side. And this E is nothing but CVT, internal energy CVT or CT, okay, specific heat into temperature. So rho C dou T by dou T is equal to rho Q dot plus all these things. Actually, it can be written as del dot K del T. And if K is constant, K can be taken out of the derivative. This will become K del square T. Okay, so dou T by rho C dou T by dou T is equal to K del square T plus rho Q dot. Is this clear? And that K by rho C becomes alpha. Okay, if I divide this, so this will become K by rho C, which is alpha. And here by rho C will be there. Okay, it depends on what units you take. Okay, so it will be written as Q double dash or Q dot or Q triple dash, like that, depending on the book. So heat generation, it will be Q dot by C. Okay, so that particular one is written as Q double dash or some other thing. And so the remaining thing you will get in this way. Is it clear?
Yes, sir.
Okay, so that is the way you will get the heat conduction equation in 3D from the total energy equation. Okay. And this is the internal energy. Okay, here we have expressed the internal energy equation. Okay, in this equation, I have tau xx, tau yx, tau zx, like that. But I want everything in primitive variables. So we know the expressions for tau xx, tau yx, tau zx. Okay, so that lambda del dot v plus 2 mu epsilon xx or 2 mu dou u by dou x, like that. If I substitute them here, I get the whole equation in this form. Okay, so this is lambda del dot v whole square and mu into 2 dou u by dou x whole square, 2 dou v by dou y whole square, like that I will get. Why? Because maybe I can write one thing, tau xx dou u by dou x. Okay. So this tau xx by dou u by dou x. So tau xx is minus 2/3 mu del dot v plus 2 mu del by dou x into dou u by dou x. So this 2/3 mu del dot v into dou u by dou x is there. And when you write tau y dou v by dou y, I will get again 2/3 mu del dot v into dou v by dou y. And again dou w by dou z I will get, which when you sum all these things, you will get del dot v. So it will become del dot v whole square like that. And similarly, here 2 mu into dou u by dou x whole square. Okay, so like that 2 mu into dou v by dou y whole square, like that I will get. And when you come to tau yx, you will get dou u by dou y plus dou v by dou x I will get. And this is again dou u by dou y plus dou v by dou x. So this into this you will get whole square. In that way, if you substitute, it is just simple thing. You are going to get this particular form. Okay, it is easy to derive this. So this already I told, these things will not change. This is the total internal energy equation with primitive variables. Only thing is, the advantage with internal energy equation is there will not be body force term. Okay, it gets cancelled. So these things I have already told. And okay, here I tell some important things. Okay, this equation, if you remember, because this is the matrix form, and so this is the total equation. All these are matrices. And here, if I want to solve this, there is what is called as time marching method. This is very, very important and very efficient. And because of this, there is a lot of progress in the CFD research. Okay. So here, suppose I have a grid and I divide into XYZ directions. So I have a grid in XYZ directions. And all these things, initially, I assume all the values, all the primitive variables at initial time. Initial condition, I know. Okay, this room is there. I want to find out the flow variables at every point as the time progresses. Okay, rho, u, v, w, p, t, all these things I want. Okay, and so initially I know what all values are. Okay, it is at some time n. And after time delta t, what it is going to become, I want to find out. Okay, so what I do is, we will do the finite difference approximation. Here, u n plus 1 minus un at ijk, at all the grid points ijk, by delta t. Okay, it is just, we call it as backward difference. Okay, new value minus old value, that is u n plus 1 minus un at all the points, right, by delta t, is equal to, I take these all these things to the right side, j minus dou e by dou x minus dou f by dou y minus dou g by dou z with ijk at nth time. Okay, e, f, g, j, all these things, all are primitive variables only, right? So we have seen that these expressions, right, all are with primitive variables. So I can calculate all the values at the point n, at time n. And using that, I want to find out how they are going to become after delta t time. Okay, so what I do is, I will write this as u ijk
n plus 1 is equal to delta t. I can take this side, and this also I can take this side, uijk n minus delta t into this. I will write it as RHS. I will write like this. And I know all these values at n and all these values at n. I can find out the new values after delta t time. Is this clear or not? If I know all the values at time some t, after delta t time, what they are going to become, I can calculate using this equation. Is it clear?
Yes, sir.
And once I know after delta t, again use them as the initial values, and again you find out the values after next delta t time. In that way, I can find out the whole evolution of the flow. That is, I march in time. Okay, marching in time after delta t, delta t, delta t, like that, I can find out what is the whole future of the whole domain. This is what is called as time marching. And so here I am calculating or updating the vector u. That's why this is called as solution vector. Okay, and what are these E, F, and G? Actually, we get it. Something is entering, something is leaving in the x direction. The difference is the some d by dx of something, right? These are fluxes. Okay, E, F, and G are called flux vectors. And J, which contains the body force and the heat generation. Okay, these two only are there. So that's why J is called as the source vector. Okay, this is the way they are named. Okay, so this is the solution vector. These are all flux vectors, and this is the source vector. It is written here. So what I am going to do is these values I am going to update after each time step. Okay, so these are the values I know initially, and after delta t time, what they are going to become, I know. I am not finding the primitive variables directly. I am getting rho, rho u, rho v, rho w, rho into v, e plus v square by 2. These are the values I am getting. But actually, I am interested in primitive variables, because rho u, v, w, v, p, and t I want. So I have to extract them. So you know rho directly from here. And how to get u? Rho u by rho. Okay, this value I know, this value I know. So dividing that, I will get u. Like that, rho v by rho, v. Rho w by rho, w. Once you get u by w, u square by 2 plus v square by 2 plus w square by 2, you will get this. Okay, rho is known. So this is CBT. C is constant, specific heat into temperature. So I can get T. So from this, I can get temperature. And I know rho, T, and velocity. And P is equal to rho RT, I know equation of state. So using that, I have to find out what is pressure. Okay. So in that way, I can so this is the way, just yeah, this is the way I will get. So rho equal to rho, u equal to rho u by rho, rho v by rho, rho w by rho w. So u v w this square by t will get this. So I will get E, I will get. E is nothing but Ct. So T will get, and from the equation of state, so rho is equal to Ct. So T is equal to rho by C, and T is equal to rho RT. So like this. Okay, this is another assumption. Actually, we are assuming that it is a perfect gas. Okay, equation of state P equal to rho RT works. Okay,
Sir,
this is the way. Yes.
E is equal to CT though, sir.
Yeah. Sorry. It is not rho, it is E. Thank you. P is equal to rho by E by rho. Okay. P is equal to E by C. Okay, thanks. Okay, this is the way we can, this is what is called as time marching method. Okay, time marching method. And
So then we talk about what are called as Euler's equations. Can anybody say what is the difference between the Navier-Stokes equation and Euler's equation?
The
In
Stokes
latest
equation.
we are considering three forces. That is,
All things will be there. Mainly the thing is these are
Viscous term.
inviscid. Yeah, very good.
Viscous term.
These are inviscid Navier-Stokes equations. They are called as Euler's equations. All viscous terms, if you eliminate from the Navier-Stokes equation, they become Euler's equations. So these becomes Euler's equations. So you can see E, F, G, H, J, like that if I write, and if I eliminate all the tau terms here, this will become Euler's equations. So again, it is simple. If I can solve it by time marching method, I can take this and I can solve this. Okay, this is Euler's equation. But here, so time marching is okay, good. But there is, suppose it is steady flow. So if it is steady flow, what happens? What is the difference happens to the equations? Why nobody is speaking?
Sir, does not change with respect to time.
Dou by dou t will be 0. Dou by dou t will be 0. Means dou u by dou t term will go off. And so I will have the equation like this. Okay, dou f by dou x plus dou g by dou y plus dou h by dou z is equal to 0. Okay, okay. EFG or FGH is I don't know just what I am writing. Yeah, FGH. Okay, like this I will get. I don't have dou by dou t term. This dou u by dou t will become 0 if it is steady. So I have only this equation. So what should I do? Now, I am marching method is very efficient and I am very much familiar and I am comfortable with it. I want to solve it by marching method. So what I do is I will try to march in space. So we call it as space marching. In one of the direction I want to march based on how the initial conditions I know. If everything is going from one face of one wall to the other side like this, I know all the conditions at one wall. So if you take that as x0 and I can find out it is like this. F I plus 1 jk minus f I jk by delta x is equal to j minus dou g by dou y minus dou h by dou z at ijk. Okay, at I equal to 1, I know all the things and I want to find out what is at the next grid point in the x-plane, I plus 1 jk. Okay, so that is the way fi plus 1 jk minus fi jk by delta x. I know all the values at I jk. At I equal to 1, I know everything. I want to find out at I equal to 2. Using that, I want to find out the next thing like that. So fi plus 1 jk is equal to fi jk plus delta x into RHS at ijk. So at ijk, I know everything. I can find out f at I plus 1. And now here this will become solution vector. F becomes the solution vector when you are doing the space march. But here there will be some problem. Okay, so what is the problem?
Sir, in space marching, the domain cannot be maybe discontinuous.
No. Domain, I first initially I assume the domain is continuous. Flow is continuous, right? There is no, that is initial assumption for the whole subject, continuum. Okay, and so here solution vector is F. F means rho u square plus p, rho u v, rho u w, like this. These are the things I am finding out. But I want primitive variables. So I want rho u v w p and t. And how to get them? So rho u, suppose this value is C1, this is C2, and this is C3, this is C4, and this is C5, I am getting it. And from this, I have to find out rho u, v, w, t, and p. Okay, these things I have to find out. How to get it? Again, in addition to this, we have P equal to rho RT is there, and E equal to CT also is there. These equations are there. And I have to extract, I have to get these values in terms of C1, C2, C3, C4, C5. So I have to do this. So this is your homework. You have to find out. But answers I am giving, but you have to find out the solution, how to do it. Okay, the answers are given in the Anderson. Okay, it is at the end of the second chapter, governing equations. Okay, this is the solution. Knowing C1, C2, C3, C4, C5, how to get rho, U, V, W, P. Okay, so these things are there. You have to find out how to get these expressions. Okay, there is a one more thing I wanted to tell. Okay, there is what is called as vorticity transport equation. In most of the fluid mechanics problems, temperature is not important. Fluid dynamics is different, fluid mechanics is different. In fluid dynamics, we had energy equation, and it is important everywhere. Usually fluid mechanics, which normally civil people teach, okay, so they will not talk about energy equation at all. Okay, so suppose T is not important. If T is not important, energy equation need not be solved. Okay, only continuity and momentum equations I have to solve. Okay. And so when you are solving continuity momentum equations, so I am going to have rho, V, and P. This and suppose it is incompressible also, then rho also is not needed. Okay, so I have V and P. Okay, so I have continuity and momentum equations. Okay, and rho is constant. Rho is constant for incompressible flow. So I have two variables and two equations, continuity and momentum. If it is 1D, 2D, 3D, momentum equations, I have to consider 1, 2, or 3. So based on that, I will have the number of equations. So here, usually the boundary conditions for pressure is very difficult to prescribe. Many times I have to find out pressure. I may not be knowing the pressures. So pressure boundary condition is difficult to prescribe. So many times we try to eliminate pressure. So how to do that? So there is one particular interesting thing people have tried. So if I take the momentum equation and okay, continuity equation del dot V equal to 0, and momentum equation rho dV by dt minus del P, and del dot tau. So this we will get it as mu del square V, because incompressible that one third del dot V, that term will go off. Okay, so mu del square V plus V. Okay, and again no body force. This will not be there. So we will get dV by dt is equal to minus 1 by rho del P plus mu del square V. And okay, this can be written as dou V by dou T plus V dot del V. Okay, d by dt is dou by dou T plus V dot del. minus 1 by rho del P plus mu. Okay, this is the way we have the momentum equation. And so I wanted to eliminate P. What is the way I can eliminate P? So from mathematicians can understand, if I take curl of a gradient, what will happen? So del cross del P, suppose.
With 0.
It will become 0. Very good. It will become 0. So what I do is, I will take curl of the whole equation. Okay. So it doesn't matter, right? So here I can write this like this. This will become dou by dou T of del cross V plus V dot del of del cross V is equal to minus 1 by rho del cross del P plus mu del square of del cross V. Like this it will become, and this becomes 0. And this is vorticity omega. And this is also vorticity omega. And this is vorticity omega. So we get like this. Dou omega by dou T plus d dot del omega is equal to mu del square omega. This is called as vorticity transport equation. This is called as vorticity transport equation. Okay, it is just vorticity is a property which is getting transported, and this is vorticity balance. Okay, so it can be velocity for momentum equation, it can be temperature for energy equation, like that we are getting, right? So this is vorticity transport equation. If I can solve this, I can get omega. Omega is vorticity. And but I am interested in velocities and pressure, right? So omega is dou v by dou x minus dou u by dou y is equal to omega. And what is u? Dou psi by dou y, and v equal to minus dou psi by dou x. If I substitute them here, what will happen? Minus dou square psi by dou x square minus dou square psi by dou y square is equal to omega. And if I write this as Laplace is, so del square psi is equal to minus omega.
Poisson equation.
Yeah, this is Poisson equation. And this is also called as stream function equation. Okay, this is another way of solving the incompressible flow equations. Okay, so for incompressible flow, we can solve in two methods. One is primitive variable method.
Another one is stream function vorticity approach.
Yeah, variable method. Another we call it as omega psi method. Stream function vorticity or vorticity stream function method. So we solve vorticity transport equation which gives me omega as the solution, and then we solve stream function equation, that is del square psi equal to minus omega. Omega is known from this equation, that is to be substituted, and I am getting psi. So once you get psi, we will get the velocities. U equal to dou psi by dou y, v equal to minus dou psi by dou x. Like this, I can solve the velocities. And once you get the velocities, you can get the pressure. Okay, so but actually I'm interested in mainly in velocities. So without bothering about the pressure, I can find out the velocity distribution. Okay, so if I want to do this, and the pressure, we will do it later. How to get the pressure from this psi and omega, we will do it later. But this is another method, and we have to know what is vorticity transport equation, what is stream function equation, what is the other method of solving an incompressible flow equation. Is that clear?
Yes, sir.
Yes, sir.
Yeah. And anything, if it is not clear, and okay, all these things, okay, this particular thing is not there in the Anderson book. It is just a general, which we'll discuss again when you solve incompressible flow equations. But till now, whatever we have done, that is there from the Anderson governing equations chapter, second chapter. And so one or two things I want to tell you. Okay. So integral equations, we have differential equations. Okay, we can put it in any form, but so people say integral equations are more fundamental. Okay, why? Because if I want to solve differential equations, the functions or the variables must be continuous. I'm not bothering talking about geometry. Okay, I'm talking about variables. Variables must be continuous. Continuous means there should not be any discontinuity. Okay, so if I have dou u by dou x, dou p by dou y, like that I have, right? So those functions must be continuous if I want to have the derivative. The main fundamental assumption in finding out the differentiation is the variables are assumed to be continuous. But there will be flows where there may be shock. Okay, so across the shock it is discontinuous. So when there is a shock, I cannot use these equations, differential equations. I have to use integral equations only. Okay, that's why integral equations are called more fundamental. Okay, more fundamental. But if I want to solve using, because integral equations I am not comfortable, differential equations in CFD I am very comfortable and I am solving. So is there now a way of solving it? So there is a way. And here, if you write in non-conservative form, we are going to get dou u by dou t, u dou u by dou x, plus v dou u by dou y. Like that I am getting. And these are derivatives which are discontinuous and they cannot work. But if I have conservation form, this is non-conservation. If I have conservation form, I am going to get dou of rho u by dou t plus dou of rho u square by dou x plus dou of rho u v by dou y. Like this I am getting. And across a shock, if I have a normal shock like this here, and there will be sudden rise in the velocity and sudden decrease in the velocity, sudden rise in the pressure, and sudden rise in the temperature, sudden rise in the density. Okay, Mach number suddenly falls from supersonic to subsonic, like this. Okay, so primitive variables will be suddenly increasing, suddenly decreasing, they are discontinuous. But if I see the continuity equation for a normal shock, if you study gas dynamics or compressible flow, so continuity equation for shock is rho u is equal to constant. And the momentum equation is equal to E plus rho u square is equal to constant. Like this you will get. Okay, so rho u square, these are continuous, no problem. Only primitive variables u, v, w, p, t, like that if you take. But if you take the products, there will not be problem. So if you take conservation form of equations, we are going to get rho u square like that. And here on the right side, minus dou p by dou x. And if I take to the left side in strong conservation form, it is going to become dou by dou x of p plus rho u square. Okay, so p plus rho u square is equal to constant. It is not suddenly changing. It is momentum equation for a shock flow. So this is the way, if you deal with conservative form of the equations, even shock flows also can be solved using differential approach. Is this clear?
Yes, sir.
Yeah. Only there is 2-3 more minutes I will take. And there are two methods called as shock capturing and shock fitting. Okay, you may not be able to completely understand. Shock fitting means if I have a flow like this, okay, this is, as I told, a rounded nose. This is bow shock. and I have supersonic flow here. And in this portion, there is normal shock, which is strong. So there will be subsonic flow. Here, this is called as oblique shock, which is weak shock. So here, supersonic will be there. But if I take this M1, this is M2. Though M2 is greater than 1, M2 is greater than 1 this side, but still M2 is less than M1. Because of the shock, there will be decrease in the Mach number. So the thing is, what I want to say is, here this is supersonic flow, this is subsonic flow, this is again supersonic flow, this is supersonic flow. And when you solve the equations, initially people found it difficult because the equations behave in a different way in subsonic flow and different way in supersonic flow. Okay, and so people used to they used to do experiments and find out where the shock comes and solve the equations before the shock using some method, and after the shock using another method, like in subsonic flow one method, supersonic flow one method, like that they used to do. That is what is called as shock fitting. Knowing the shock ahead of the numerical calculations and fitting the shock in the calculation is called as shock fitting. But if you can find out where the shock comes with the numerical calculation, and this could be done after time marching method came into picture. Okay, that I will explain. So using time marching method, if I can solve the direct equations in a single method, and if I can capture the shock where the shock comes, right, that is called as shock capturing. Could I make a difference between these two? Knowing the shock ahead of the calculation and fitting it into the calculation is called shock fitting. Shock capturing is using numerical calculation. If I can capture or find out where the shock comes, that is shock capturing. Is it okay?
Sir, how does this capturing like take place?
Okay,
here?
that we will do in the next class. Okay, we will discuss about this.
Okay, sir.
Okay.
Sir,
Yes.
sir, what is shock?
What is
Shock.
shock? Okay. If there is a supersonic flow, right? If there is any disturbance or if there is any body, there will be sudden drop from the supersonic to subsonic. Okay, and so there will be a sudden change of velocity from supersonic to subsonic, and it is discontinuous. And because of sudden decrease in the velocity, there will be sudden increase in the pressure, density, and temperature. Okay, that is called shock.
Okay, sir.
Okay, and the initial classes I have talked about attached shock, detached shock, sharp nose, rounded nose, those things. Okay.
Sir,
Yes.
sir, for incompressible flow, also
Yeah.
rho may not be constant, sir, because if
We
I take
call the flow to be incompressible only if rho is constant.
sir.
Okay.
But for incompressible flow, rho or may not be constant.
No. Incompressible flow is rho is constant. But if you take subsonic and supersonic, in subsonic flow, rho may be changing.
Okay.
Okay, up to Mach number 0.1, they see Mach number less than 1 and less than 0.3, m equal to 1, m greater than 1, like this. So up to my Mach number 0. 0 to 0.3, the rho is constant. I don't consider the variation.
Okay, sir.
I assume it to be incompressible. But here to here, there will be changing. In subsonic, there will be rho changing. In supersonic, there will be more changing of density.
Okay, sir.
Okay. So 0 to 0.3, I assume rho to be constant and it is considered to be incompressible only. The change in density is negligible.
Sir, that Mach number up to 0.3 derivation, we'll assume that variation should be less than 10% something. No,
5%, less than 5%.
5%, yeah.
Yeah. Actually, that we can prove it like rho naught by rho is equal to 1 plus gamma minus 1 by 2 m square to the power of 1 by gamma minus 1. Like that, if you see. So rho naught is the maximum one. And Mach number up to 0.3, if you take the density, so rho is equal to rho naught by this, right? right? For a given rho naught is constant, and with the Mach number changing, if the rho changes, so up to Mach number 0.3, if you see, the rho value from the rho naught variation is only less than 5%. That's why I can consider it to be incompressible.
Sir, this conservation, non-conservation,
Yeah.
other than coding part, is there any other physical significance, sir?
There is nothing like that.
Oh.
In that form, whatever is there mathematically, if there are no coefficients for the derivatives, it is called as conservation form. But mathematically, the advantage in capturing the shock we have for conservation form of it.
Okay. Thank you.
Representation itself, we call it as conservation form, non-conservation. Okay. Anything else? We'll have the story quickly. Nice, interesting story. So it is stories from a 500 rupee note. There are two small stories. I have received the following two lessons which I want to share with all of you and hope you will find it useful. First lesson. It happened some years ago, but I can recall the evening like it happened just last week. I was in an audience listening to a motivational guru. The speaker whipped out from his wallet and pulled out a 500 rupee note. Holding it up, he asked, "Who wants this 500 rupee note?" And lots of hands went up, including mine. And a slow chorus began to build as people began to shout, "Me, me, me," like that. Everybody shouting, "For me, for me," like that. I began to wonder who is the lucky one would be who the speaker will choose. And I also secretly wondered, and if I am sure others did too, why he would simply give away 500 rupees. How can you give just like that? Maybe just making fun. Like that, he thought, and maybe many people are thinking. But even as shouts of "I want it" grew louder, I noticed a young woman running down the aisle. So one lady went running away to the dais. She ran up onto the stage, went to the speaker, and grabbed the 500 rupee note from his hand. She has taken it. "Well done, young lady," said the speaker into the microphone. So most of us just wait for good things to happen. That is of no use. You have got to make things happen. The speaker's words have stayed with me ever since. Simply thinking about it, doing something is of no use. It is like dreaming, right? So it is of no use. Our lives are like that. We all see opportunities around us. We all want the good things, but the problem is we don't take action. We all want to have that 500 rupee note as an offer, but we don't make the move. We look at it longingly. If I get it, it will be good like that, we'll think, but we are not doing the action. Get up and do something about it. Don't worry about what other people will think. Take action. Okay, this is the first story. Another small story. Several years later, it was another day, another time, and another motivational guru came. And as I watched him pulling out a 500 rupee note again and hold it up for all to see, I thought I knew what he was going to do next because I already have attended. But he just asked a simple question. It has gone in another way. He told how much it is worth. And 500 rupees, the crowd yelled in unison. Right, said the speaker. He then took the note and crumpled it into a ball and asked, "How much is it worth now?" 500 rupees, screamed the audience. He then threw the note on the ground, stamped all over it, and picked it up the note and asked one more time, "And how much is it worth now?" Again, all people told 500 rupees. And he said, "I want you to remember this. Just because someone crumples it or stamps on it, the value of the note does not diminish." We should all be like the 500 rupee note. In our lives, there will be times when we feel crushed, stamped over, beaten, but never let your self-worth diminish. Just because someone chooses you to crush, that doesn't change your worth one bit. Don't allow your self-worth to diminish because someone says something nasty or does something dirty to you. never let your self-worth diminish. Okay, these are the two lessons I would like to share with you. Okay, thank you very much. All the best. And one more thing, okay, before leaving, I am going to send you another book by Chopra. It is Numerical Methods Using MATLAB. Okay, it's very interesting book, worthy book. And here, second and third chapters, he has given some MATLAB how to practice. Okay, instead of Rudra Pratap, now you go through this book. Okay, go through the second, third chapter. You practice those commands, and there is a chapter on solving the algebraic equations, the Gauss elimination method, Gauss-Seidel method, and tridiagonal matrix method. There are three methods to solve the linear equations. You go through those functions. Functions are written there. You try to understand what is the method, because you already know numerical methods, how to solve Gauss-Seidel and Gauss elimination, and how the program is written. You try to understand the logic. So tomorrow we will discuss about them, and we will solve those problems. Is it okay? I am sending the book to you. And yesterday's video, still it is not, it has not come. It is still processing. I didn't post it, and I will post that and this to you. Anything else to ask or talk? Okay, if there is nothing, we'll meet again tomorrow's afternoon class. And the PhD students, if you are interested, you can attend the lab class also with the same link. Okay, tomorrow afternoon,
Yes,
2
sir.
to 5. 2 to 5. Okay. And you also try to install MATLAB if you don't have the student version, right? I have sent, I think, CFD Lab 1 lecture. Their instructions are given. You can just install it, or you take help of one of the student here. If you want any contact of one person, I can give it to you. And maybe Dipanshu or Bharat, you can help him, I think, help these people if they ask.
Okay, sir.
Okay.
So I will try to give your email ID to them, right? If there is any difficulty, I think all of them might have used the mathematics people. You know, MATLAB usage of MATLAB.
Yes, sir.
So if you know, there is no difficulty at all. Okay?
Thank you, sir.
Okay, thank you. See you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.